Hi, this is Crossdot and Nabla, and in today's section, we're going to be covering over topic 12.8, Maxima and Minima. This video is going to be a little bit different than what we've learned about Maxima and Minima in Calculus 1, but there are a couple of similarities that we would like to go over real quick, just going back to Calc 1, remembering what are critical points, how do we solve for maxima and minima, right? So we have critical points where f prime of x equals 0 or D and E are candidates for determining local mins and maxes where that can occur. We can use the second derivative test to determine concavity, right? For whether or not a critical point is a local max or min, right? In this case, since we know this function is a concave up, for example, we can say f double prime is greater than 0, therefore local min, right? And if this was going downward, f double prime is less than 0, therefore it's a local max, right? So there's some familiar ideas, hopefully from Calculus 1 that we can recall and are actually going to be applied with partial derivatives instead of just taking the derivative with respect to a single variable function, right? And we know that global maxes and mins on a function on an interval can occur at a critical point in the interior or at the endpoints of the interval. So going to an example, let's just get something like this. Let's just draw some blue. We have some right here. And we want to determine where there were critical points, maxes and mins, both global and local, to determine this, right? So just by looking at this, we have to test points from within. We see that, just write this in red, right here's global, local min, local max, local min, local max right here, local max, and then you test all these points to see, right? Just by looking at the graph, we know this end part right here is going up. We know this part right here is going down after, right? And then we can test the actual values after we take the derivative, right? We take the derivative on the interior, right, to solve for 0 and see where the function would have its x values at, right? However, in 3D, if we're looking at our endpoints, these aren't endpoints anymore because we're considering multiple variables now. We're considering x and y. So if I draw something like this, if I draw like a paraboloid, I have to consider the entire boundary. I can't just consider a single coordinate axis, right? And that's kind of the idea of extending this into 3D, right? Extending the idea of maxima and minima into 3D. Now, we're going to go to this in 3 dimensions, right? Like I just mentioned earlier. For extreme values, f is a global maximum if the point a comma b, if f of a comma b is greater than or equal to f of xy for all xy in the domain of f. But we're just going to be writing this down for the comparison to it being in 2 dimensions. If f of a is greater than or equal to f of a for all, and actually this should be for all x, as a local maximum at the point a, if for all x, f of a for all x near a, right? And it's just like taking the limit as you approach that value, right? Global minimum, it's the exact same idea. And here we can more easily, this is a salient picture that can help us identify local and global maxes and mins in 3D, we see right here, this is our absolute max, absolute min, relative max, and relative min. One other thing to note though in this case is that often in graphs like these, looking for symmetry is one of the most important things you can do to solve for these types of problems, right? Because in this case, the graph is symmetrical along the XY axis, right? That's important to note as well, just to save yourself some time solving for your critical points. We have critical points now. Letting F be defined as a set containing, on the interval, containing A comma B, the point, right? If F of A comma B is an extreme value, then A comma B must be a critical point. We know this from Calculus 1, where we say, if we have a max or min, the derivative has to be 0, right? It's a critical point. That's how we define it, right? There has to be a boundary point. So a boundary point is like what we mentioned earlier, is if we know it's lying on some boundary, like could be like a circle or a square, a rectangle, triangle even, right? We don't know. It's still important to know that you have to look for that. And it's like the 3D extension of saying that your endpoints on the interval, now it's your entire boundary, because you're not only bounded by the x-axis or only one axis in general, you're bounded by two separate axes, right? And that's where it gets a little bit more tricky with these types of problems. A stationary point where the gradient of f equals a 0 vector, where the tangent plane is horizontal. So that's just like if you have parabola, for example, the origin, like if it's like x squared plus y squared equals z, then your stationary point would be 0, 0, 0, 0, because everything else goes up around it, right? And it's a singular point of s where f is not differentiable. So that leads to like the jumps, discontinuities, vertical asymptotes, things like that, right? And one other thing to note, critical points, again, are also candidate points, which we've covered again in Calculus 1, for both global and local extrema, global and local maxes and mins, right? Now we go to another theorem. If we have f continuous on a closed bounded set S, then f attains both a global max and global min value there. Again, this is kind of straightforward from what we understand from Calc 1. If you have, it's like the mean value theorem, intermediate value theorem, basically extended over to 3D, because even if you have like a straight line, right, it's going to have both a local max and min. It's at the same value, right? It's kind of redundant to say that, and you wouldn't say that, right? But looking at that, we can understand a lot of the ideas are similar from 2D to 3D, right? Now we have our second partials test theorem. It's harder for us to determine whether or not by looking at the first partials. So we have to take the second partials to make sure that it is going to be concave up or concave down at that point. And the work concavity I don't even particularly like, because these 3D graphs, as we'll show in this video, curve and turn and move in really weird ways that you wouldn't anticipate just by thinking about it in your head, right? So that's why we have the second partials test, and it's like a long derivation. It involves Taylor's theorem. I had to look this up before I started the video. It was like Taylor's theorem and some complicated math that we're not going to go over to prove this. But this idea is really, really important to determine your maxes and mins along this set, right? Or along these boundaries, right? Or just in general for the function itself. So suppose that f of xy has continuous second partial derivatives in a neighborhood of a comma b. The gradient of f of a comma b equals 0. It's a 0 vector, right? We let d equal to d of a comma b be equal to the second partial at a, second partial with respect to x, a comma b, second partial of f with respect to y, a of b, and then the second partial of x, y squared minus a, b. This, remember, is also just equal to negative. Those two are the same thing, right? Those two are the same thing, and we've shown that before in our previous section, section 12.4. And looking at this now, we have our d value being greater than 0, and your f sub double x, f double prime with respect to x. F double prime doesn't work really. It's the second partial of f with respect to x both times. Or I can just say f sub xx, whatever works. A comma b, then a and b is a local max, right? So basically this is the kind of like concavity link, because again, I guess we can imagine it to be like going like this. Right here is our max, it's concave down, you know, technically that works, right? Same thing for the second statement, that's also true with respect to this. Like if you were to do it like this, technically that's true, but like it's not really the same idea, right? Because concavity in calculus 1 just only refers to looking at one variable, but now in calculus 3 you're looking at multiple variables on a graph, right? Third statement, if d is less than 0, then f of a comma b is not an extreme value, it's a saddle point. And on Desmos, we'll actually show what these saddle points look like on these curves, right? And number 4, if d equals 0, the test is inconclusive, which means we have to test in some other ways, right? But yeah, that's what the second partial test does. It's kind of like using your second derivative test to prove concavity if you're not 100% sure, right? And yeah, for example 1, let's do this example together because this is the first time seeing a problem like this and it's going to be kind of tedious to work it all out. And let's get right into it. So we have f of xy equals xy squared minus 6x squared minus 3y squared. Find all critical points indicating whether each is a local min, max, or a saddle point. So given our steps, we have to take the gradient of this. So then we're going to take the gradient of f of xy. And then we're going to get, this is a vector operation, so it's going to be that y squared minus, no, it's not going to be y squared, it's going to be 2xy, no, oh my gosh, no. It's supposed to be y squared minus 12x, 2xy minus 6y, and you want this to be a 0 vector, right? So let's start off by using this one because this one looks easier to solve for. So you have 2x, actually, no, we want to factor out the y. 2y, x minus 3 equals 0, so we know that y equals 0 or x equals 3. That works for either one. And then let's just try and plug in y equals 0 for this one. So we get y squared minus 12x equals 0. So plug in 0 here. 0 squared minus 12x equals 0. 0 equals 12x, x equals 0. So we have our first point to test is 0, 0. And then our second point we can test is x equals 3. And the reason why we're just plugging in these values is because what we want is a 0 vector, right? Instead of it just being 0, it's going to be a 0 vector because we're taking the gradient, and the gradient, again, is a vector operation like the cross-product dot product, right? Now, plugging in 3 into our equation for x, we get y squared minus 12x. I'll just write when x equals 3, when x equals 0. Well, actually, let me write that up here. When y equals 0, yeah, equals 0. So we have y squared equals 36, because negative 12 times 3 is negative 36. Yeah, 36 to both sides. Y equals plus minus 6. And then we get 3 comma 6, 3 comma negative 6. And now we can use our second partials test to solve for this, right? So we have our first partials right here, and we can just take the second partials real quick. So we have f sub x equals y squared minus 12x equals negative 12. F sub y equals 2xy minus 6y. F sub yy equals 2x minus 6. And now we can solve for f sub xy. We can choose either one, doesn't matter. I'll just choose the first one, which will get us equal to 2y. And then we can plug everything in. So we have d of a comma b, actually no, not a comma b, d of x comma y equals negative 12 x minus 3 minus 2y squared. So d, that's right, case 1, 0, 0. So we have d of 0 comma 0 equal to negative 12 comma 0 minus 3 minus 2 times 0 squared. So we're going to get negative 12 times negative 3. Oh, wait, no, that's not. Oh, it's supposed to be negative 6. I forgot. Yeah, because I thought, yeah, that's my bad. But that ultimately still wouldn't change the result. Oh, it's supposed to be 2x minus 6, yeah. So it wouldn't matter in this case, but just to make sure that we have that consistent throughout, it'll make the math a lot more easy to look back on. Minus 0 squared. So then we have this to be 72 minus 0, which is greater than 0. However, we have to also check if the first partial is less than 0, the second partial is less than 0. And so we can check that off real quick. This works. Check f sub x of x equals negative 12, which is less than 0. Check. Let's write this. Therefore, 0, 0 is a local max. Perfect. Case 2, 3 comma 6. So it's going to be d of 3 comma 6 equals negative 12 times 2 times 3 minus 6 minus 4 times negative 3, positive 6 squared. I was looking at that third example real quick. Oops. This is going to go with 0. So we're going to have 0 minus 144. Negative 144 is less than 0. So that's a check for us. Now we need to check, since this is less than 0, we have to make sure that the second partial with respect to x is greater than 0 at this value. And in fact, oh, actually, no, we don't have to check it. So it has to be greater than 0 for local maxes and mins. It has to be a saddle point, actually. So now we caught that, actually. That's perfect to catch that. Therefore, 3 comma 6 is saddle point because d of 3 comma 6 is less than 0. And then case 3 comma negative 6. We can do the same thing. We have d of 3 comma negative 6 equals negative 12. 2 times 3 minus 6. Again, this goes to 0. Minus 4 times negative 6 squared. This is negative 144, which is less than 0. That's a check for us. Therefore, let me just be consistent. Let me just be consistent and write in red, because I like to do that. 3 comma negative 6 is a saddle point because d of 3 comma negative 6 is less than 0. And now we can look on Desmos to see whether or not the math backs up the actual graph, right? And we can see, looking at this is the same graph that we had before. We can see the things that we saw were actually true, right? So we see for these green dots right here, we have them to be the saddle points that we were anticipating, right? Where if you go in one direction, you'd be going down, but in another direction, you'd be going up. So like in this case, right here, if this dot were to go up, and I kind of just killed the graph right there, but if this dot were to go up in the direction towards the blue dot, you'd be going up. But if it was going down in this way, see the way I'm jiggling it? This way, it would go down. And then the blue is a max because around all directions, in fact, it would actually be going downward, right? That's why the second partial with respect to x is negative at that value, right? And that's something important to note as well. So we both proved it mathematically and graphically just by showing this, right? And we plotted the points as well. In this case as well, the 6 is going to be symmetrical with both of these. 6 negative 6 are going to be symmetrical, so that's why they're the same y value or the z value, right? And that's how we showed it graphically for example 1. Now, going to example 2, we want to find the global max and min values for this function on this interval. Now, not only are we going to be testing points within the boundary, but we're also going to be testing points from along the boundary, right? So we have to be conscious of that. Feel free to try this one on your own and pause the video, and let's get right into it. So take the gradient of f of x, y. We get 2x comma negative 2y. Need this to be a 0 vector, so it's going to be 0, 0 as our interior point. We'll just do f sub xx equals 2, f sub yy equals negative 2, f sub xy. So I'll just try f sub x first. 2x partial with respect to y is 0, so that's going to equal to 0. We have d of xy, case 1. We have d of xy equal to 2 times negative 2 minus 0. This is negative 4. Therefore, a saddle point because d of 0, 0 is less than 0. Right. Perfect. Now, however, we're going to be looking at the boundary points now because we couldn't find anything else, right? We got to test everything to make sure that we don't have any local mins or maxes along this curve, right? So we have on our side, we have 1 point, we have a saddle point. Now we have to do a little trick of algebra to make this function a little bit easier to solve for. So we have our boundary, it's a circle, right? X squared plus y squared is less than or equal to 1. We know that, that's not too terrible. However, what we have to do now is isolate for y squared, right? So we're gonna get y squared is less than or equal to 1 minus x squared. And now we can substitute that into here in this equation. So we're gonna have f of x now, because it's only one variable, f of x equals x squared minus 1 minus x squared minus 1. F of x equals 2x squared minus 2. And remember, we're operating on the interval, negative 1 to 1 for x, right? This is still the same thing as this. We're just replacing y squared with 1 minus x squared, right? And remember that x squared plus y squared is less than or equal to 1. It's a unit circle, negative 1, 1 right here, right? That's important to note for this problem. Now we can actually graph this. We can graph it on Desmos, or we can just intuit this on our own. We start at -2 here. We start at 1, 1 here. And that's -1, 1. Now we have our points that we can look at and identify. Okay, now we can solve for our endpoints, right? So right here, we have -1, 1, 0, and then we have 0, -1. We have 0, -1, or 0, 1. Either way, that would get us our case statement, right? Looking at what we had, these cases right here are kind of obvious just by looking at it. We know that it's going to be 0, -1, but for 0, 1, what we have to do for that is look at symmetry for the case x equals 0, right? So if it's x equals 0, that means it's also going to be going up to here as well, and we'll show that later on in the graph, right? Or if you can just even if you plug it into here, we get 0. We plug in 0 here. Y is going to equal plus or minus 1, right? Actually, that's the best justification you can have. So you're going to have y squared is less than or equal to 1 plus minus 1. So that means that it's going to be -1 is less than or equal to y is less than or equal to 1. Right. So that's also another way you can think about it as well, allowing us to get 0, 1. And now for here, we can plug it into our equation to just solve for the our local mins and maxes. However, we don't have to do that. We can't really do that with this case actually, because no matter what we do, we're just going to get -4 as our final answer. However, we can look at our graph again and say that we know that these are maxes right here. So these are maxes. And then right here, these are going to be mins. And if we plug them into our equation right here, we have 0, let's just try 0, 1, 0, -1. Regardless of the y value, same magnitude, right? It's going to be 0 minus 1 minus 1. It's -2. So it's going to be -2 for those z values right here. So we'll just say z equals -2. And then -1 and 1 doesn't matter for the x value. It's going to be, you square that, it's going to be 1. 1 minus 1 is 0. So we'll just say that z equals 0. Perfect. Now to make sure, we can check on Desmos to make sure everything looks up to task. Now we're looking at our equation, and one thing you can do on Desmos that's nice is you can actually zoom it out kind of nicely to see it. And in this case, this is looking a little bit off. Yeah, make it a perfect circle right here, yeah. And it kind of looks like a Pringle chip, actually, if you cut and slice it a certain way, which is pretty cool. I think that's actually how the people at Lay's made their Pringle chips. They actually made it off of a hyperboloid, which is, in my opinion, really, really cool. But yeah, looking at this, we have 0, 0, -1 as our saddle point. Our when y is equal to 0, we have our maxes, and then when x equals 0, when x equals 0, we have our maxes. When y equals 0, we have our mins. We have 2 global maxes and then 2 global mins, and we have 1 saddle point, right? And remember that global maxes and mins are also your local mins within this region, right? And yeah, that's, again, we're showing how we can use Desmos to do this. One nice thing with Desmos is that you can actually write with the squiggly brackets to have it be the entire circle, so you can't write it separately like x squared is less than equal to 1 or y squared is less than or equal to 1, because then it treats it as an or statement, not an and statement, right? For example 3, we want to now find points where the global maximum min occur for this paraboloid on the set S. And if you want to try this on your own, feel free to pause the video. And more importantly, let's get right into it. So again, let's just always take our gradient. Our zero gradient is going to be 0, 0. So we have case 1 already down. And now for each of these boundaries, last time we had a circular boundary, now we have a rectangular boundary. The only difference now that you have to really worry about is just plugging in at each of these respective corners. And the reason why you would plug in at each of these respective corners is because, for example, for the y values, right, the lowest you can go is -1. So just plug in -1 to see if there's a max or a min at that location, right? If you plug in 4, for example, that's bigger than any other value, right? And if it's y squared right here, 4 squared is 16, right? That's going to be way bigger than anything else, right? Same thing for -1 to 3, the same idea. You're going to be squaring something that has a greater value along that interval, right? So we can actually just do that real quick and get this. For 0, 0, we got case 1, 0, 0, 0 squared plus 0 squared is just 0, so we have our 0, 0, 0. And then for f of -1, -1, we have -1 squared plus -1 squared equals 2. So we have, and then we have f of -1, 4 equals -1 squared plus 4 squared equals 17. Then we have f of 3 comma -1. It's a lot of algebra, not even algebra, it's arithmetic, but same idea. And then eventually you're gonna get to 4 as your answer. And the reason why you can do it for this type of problem is because it's a rectangular boundary, and these functions are going to be strictly increasing, or their behavior is going to be easy to predict, right? It's like a basic polynomial. So when you plug in at the endpoints, you can actually see where the maxes and mins would be along that curve, right? So like, for example, if we just keep it stationary at 3, right, at x equals 3, we can then just say that it would be f of y equals 9 plus y squared, because we know that x equals 3, we're holding that constant. And if we're going on the interval -1 to 4, then we can just plug in values for y to see what would be the greatest for that, and we can do that for all these different values, right? And that's ultimately what we're doing, but rather just focusing on those endpoints, because we know those endpoints are going to be the greatest value in magnitude, right? And then from all these cases, we see that 3, 4, 25 is our global max. And then we have 0, 0, 0 as our global min. And then the rest, I believe, should be local maxes. And we can check in Desmos. Yeah, so now we're looking at this paraboloid in 3D Desmos. And one of the cool things is we can see how we have all these local maxes right here. We have the green one right here, which is at 10. We have the gray one right here, which is at 17. And we have the purple one down here, which is at 2. However, this blue one right here is way, way, way bigger, right? And that's because its radius is the largest out of all of them as well, right? You can think of it like that as well. Its radius is going to be the largest, because it's going to be a circle, right? X squared plus y squared equals f of xy, right? This radius isn't as large, it'd be like root 10. This radius is going to be root 2. This radius right here is root 17. This is root 25, the largest. However, at the origin, which is going to be 0, 0, 0. Red's not the best color, so let's just use orange instead. Orange right here is our global min, because if we did 0, 0, 0, that's the lowest value on this interval. And even if we did the second partials test, we would get 2x, 2y. It would be 2 times 2, which is 4 minus 0. That's greater than 0. And then you can test the second partial with respect to x being greater than 0, which it is. Then you can also say that's a local min 2, which we did test as well in our example, right? So you can look at it both graphically or mathematically to say, like, okay, now we know what our maxes and mins are on this graph. And then last but not least, example 4, find a 3D vector of length 9 with the largest possible sum of its components. Try this one on your own, and feel free to pause the video. All right, so for this one, this is going to be covered over in our next section called Lagrange multipliers. This is still a good one to try, though. I would recommend this one. It's a nice, like, little brain teaser. We have some vector operation like this. Oops, my pen just died. Just fixed it. And you have this constraint, but it's going to be a sphere of radius 9. You want to maximize it, right? And one obvious thing you can look at is if you want this to be maximized, what you can do is you can just say that x equals y equals z, and you can just say that be x squared plus x squared plus x squared equals 81, 3x squared equals 81. No, not 81, excuse me. Oh, so many mistakes today, wow. And you get x equals 3 root 3. And that meets both the criterion here and the criterion here. And in our next video, covering over Lagrange multipliers, in fact, what we'll do to prove this is by using a constraint with lambda, and lambda would basically work as a way to check for values that would maximize this this constraint, right? Because we have multiple constraints here. We have this right here, and we have this right here, right? And you have to make sure that both of them are maximized to get the greatest possible sum for its components, right? And that is it for section 12.8. Thank you so much for watching, and I hope you guys have a great day.